So differentiability is basically, when we talk about functions, can we take the derivative? Okay, so there are certain places, and this that I have here, this is actually data or 3D data that's been rendered by Schlumberger. It's a company that does oil and gas. So this is actually three-dimensional data from the bottom of the Gulf. Okay, so all right, so to be differentiable, a function must be continuous and smooth. We talked about that on Monday. So differentiability in a function means that it is smooth and continuous everywhere. Okay, so today we're going to talk about where a function is not differentiable. Okay, so derivatives will fail to exist where it is not continuous or it's not smooth. So the first is basically at a corner. Okay, our absolute value function is a perfect example of where a function is not differentiable. Now, the absolute value function is differentiable everywhere except for at 0, at this point where it is not smooth. Okay, same thing with a cusp. You know, cusp, yes, you have. This is how you used to draw birds. Like when you do it in an art project and you draw a bird and you go, ooh, ooh, that's a cusp. You've been drawing them for a while. Okay, now, a cusp, again, just like a corner, is not smooth. So it fails to be differentiable there. Okay, so at this point, it is not differentiable. It's differentiable everywhere else, but not where it comes to this corner, this sharp point. Okay, now, the other place that derivatives fail to exist are when we have what we call a vertical tangent. Okay, so this right here is a vertical tangent. So if you watch the slope, this is the 1/3 power or the cube root. As it goes along, this right here, you've got this positive slope, positive slope, positive slope. When it gets right here to 0, that tangent line goes vertical, and a vertical line has undefined slope. And since the derivative is slope, if the slope is undefined, the derivative is therefore undefined. Okay? Does that make sense? All right. And then, of course, the last place when we talk about differentiability is where there's a discontinuity. If the function is discontinuous, it can't have slope there. Okay? Not that we can find. All right? So these are the main things that we're going to be dealing with this year in calculus. Okay? Again, most of the functions that we're going to be dealing with this year are going to be differentiable. There are going to be a couple of times where they're not. Now, the calculator. There are calculators that will do calculus. The Inspire that we use does calculus on it. Okay? But here's the problem. Just like any other time you use a calculator, if you don't know what you're doing, or if you're asking it to do something and you don't know that it can't, it will give you wrong information. For instance, if you put in -4 squared into a calculator, it'll say -16, unless you put it in parentheses. Okay? Same thing with derivatives. Even if a calculator will do derivatives, sometimes it lies to us. For example, this one, if you put this into your calculator, this is the reciprocal function, 1 over x, and I'm asking to find the slope or take the derivative at 0. It's going to return negative infinity, or it's going to return positive infinity. But the reciprocal function at 0 has an asymptote. So how is their slope, and how is the slope negative infinity? How do you even draw that as a slope? Rise over run, guys. How do you draw negative infinity as the rise and 1 as the run? Does that even make sense? Okay. That doesn't even make sense. So this is what the calculator will return. Also, we just talked about it, the absolute value function. If I plug it in the calculator, it's going to return +1 and -1. How can it have two slopes? It can't. So again, what it's doing is it's evaluating, the calculator is actually evaluating it as a limit, and it's giving you either the right hand or the left hand side. Or in this case, the absolute value, it'll give you both. So be careful. The calculator's a liar sometimes. You can't trust it all the time. It's programmed by people, and then it's only as smart as the person using it. Okay? So if you don't know what you're doing, it's not going to know what you're doing. Okay? All right. So 2 theorems we're going to deal with. If f has a derivative at x equals a, then f is continuous at x equals a. Okay? This is really important. This is the inverse of the differentiability theorem. Okay? Differentiability says if it's differentiable, it is smooth and continuous. This is saying, oh, if there's a derivative at a point, then that function has to be continuous there. Okay? Such functions must be continuous to have a derivative. The derivative is then continuous. Okay? And the intermediate value theorems for derivative. We've dealt with the intermediate value theorems for numbers, just the IVT. This is the one specifically for derivatives. All of this basically says, just like the intermediate value theorem says, that if I have a function and I know the slope at one point and I know the slope at another point, that this function has to take on every single slope value between. So if I know my slope right here at A is 1/2 and the slope at B is 3, I can't get from that slope of 1/2 to 3 without going through the slope of 1, the slope of 2, the slope of 2.5 to get to 3. Okay? So if you know the slope at one point, you know the slope at the other point, and again, this is an existence theorem, it's telling me that I know all of those points in between exist. Now, it only guarantees the points in between, the slope between A and the slope at B. And that's how you read this. If A and B are 2 points in any interval on F, and it's differentiable, then F prime, which is what? Slope, the derivative, takes on every value between those two slopes.